Okay, what did you all think of that quiz? Was it all right? Let's take a look at it. I won't normally go through every quiz that we take in class just because of time, but since this is our first one, I will. So the left-hand limit, number 1, what I was looking for was for you to write lim x approaches -3 from the left of the function f of x equals, now what is it approaching as we approach -3 from the left?
3.
It's approaching 3. All right? And then number 2, limit x approaches -3 from the right of the function equals what? 1. Okay, so this is what we covered last time, coming into 3 from the left and 1 from the right. And then number 3, what do you think I wanted you to write for number 3? F of -3, right, equals 1. Okay, so that was the first 3. The fourth one is another left-hand limit. Limit x approaches 0 from the left. Right, that's what it was. And as I approach 0 from the left, where am I headed? 4? Okay. And then what is the limit as x approaches 0 from the right? It's also 4. And then for number 6, f of 0, which is undefined. All right, so far, it's not defined, right?
I wrote none.
None? Yeah. Oh yeah, by the way, this class was, it was getting a little too quiet. Y'all weren't being very responsive, so I had to call in the big guns. Jason has joined us here this semester, so he's here to keep us
Lively.
entertained, shall I say?
Thank you.
Okay. What's that? Zach would probably get us a little worried. Yeah. Okay, left-hand limit, x approaches 3. Negative again, right? Little minus sign there. And what is the limit as we approach 3 from the left? 2. Okay, so here's 3. We're approaching it from the left side, so we get, am I on the right problem? Yeah. Okay, so f of x equals 2. And then number 8, limit x approaches 3 from the right of the function. What is it from the right? So this is 3, we're approaching it from the right, so we're on this part right here, which is doing what? It's oscillating. We did that one problem, remember, where it oscillated like that and went crazy? Do you remember that? And what did we say in that case? Does not exist. So even though I put a hole here at -6, the fact that the function goes up and down means it's impossible for me to do it, like very accurate. I did the best I could, but that matched kind of what we did in class. That oscillation means that the function is not headed towards a specific value, and therefore the limit does not exist. All right. Number 9, what's the value of the function at 3? So that's just saying what's f of 3, and that is -2. Okay, so that's it. So if you have any questions over that, like you're still not understanding all this, you need to make some time to come by my office. Remember, I'm after class, I'm in my office, so come by, visit. But now this is behind us. I'm expecting that you understand that, and we move forward. All right, so what we're going to do now is we are going to do maybe two more problems similar to what we were doing last class. The limits that we ended with, which were kind of weird. We only did one example, and so I want to do another one of those. Let's try this. Let's, as an example, take the limit as x approaches 0 of tangent of 5x sine of 3x over 4x squared. All right, so this is, we're back into where we ended class, which was we're trying to evaluate limits without looking at the graphs. You know, when we have the graphs, it's usually pretty straightforward as far as looking and just figuring out what's happening. But without the graph, can we figure out what's happening as x goes to 0? So the first thing we do is try and do direct substitution to see what form we're getting, all right? So let's do that. What happens on the top? So if I plug in 0 here for x, 5 times 0 is 0, and tangent of 0 is 0. So we get 0, top left is 0, times sine of 0 is also 0, so we're getting 0 times 0 on top, and on the bottom 0 squared is 0, so we just get 0. So we have the form 0 over 0, right? And this is that bad situation that we had. And anytime we see that bad situation, we're either going to do some algebra or some sort of trick, some sort of manipulation that's going to make it work. So last class, the problem I did at the very end, what was the thing that I was using in order to make it work? There was some very special limit that I had to always keep in mind I could use. I told you had to memorize it, that it was something it was this one right here. Limit x approaches 0, sine x over x equals 1. And I told you, you know what, that's great, but let's look at it this way. Limit, who cares what's happening with the limit, right? Who cares about this? Sine, and I said sine of some junk over some junk, right? And I told you that as long as these junk things matched exactly, and as long as these junk things go to 0 when you take the limit, that the answer to this is 1, right? That's what I was trying to get you to see last class. All right, so when we see this bad situation, there's no sort of factoring we can do. There's no difference of squares. There's no nice algebra that we can do to this. So our only hope is to try and do what I did at the end of last class, which was to kind of rip this entire thing apart and try and identify where the bad situation is occurring. And before I get to that, I want to just remind you of a couple of things that came up at the end of class last time. Just want to make sure everyone's clear. If I take sine of 3x, this is not the same as 3 sine x. In other words, you can never factor out constants from inside of the argument of a trig function. You can't do this. If that were the case, this would become a much easier problem. But since we can't do this, we have to proceed, okay, without this sort of thing, right? Okay, so let's move on. I have this bad situation. I'm going to start this out by rewriting the limit, and then I'm going to start peeling this thing apart. And watch the way I do this. I'm going to go tangent 5x over 1 times sine 3x over 1 times 1/4 times 1 over x times 1 over x. So like I've totally ripped that whole thing apart. I've expanded it all out so I can see every single little piece of it. Do you all agree that that's the same exact expression? Yes? Okay, I'm going to go one step further, all right? I'm going to go one step further, and I'm going to remember that tangent is sine over cosine, right? So I'm going to rewrite this. Limit x approaches 0. I'm going to write that as sine of 5x over 1 times 1 over cosine of 5x times sine 3x over 1 times 1/4 times 1 over x times 1 over x. So it's the same expression that I had here, except instead of writing tangent 5x, I wrote sine over cosine, but then I pulled those two apart and did it sine 5x over 1 over cosine 5x. Does everyone see that it's just the same problem? Okay, now let's go and identify where we're having a problem. And remember, the problem for us is always the division by 0. I mean, 0 over 0, yes, that's bad. But the division by the 0 is really like what's steering us here. So how can we eliminate that bad situation? So I actually get division by 0 with both of those, don't I? If I let x go to 0, both of these are going to become undefined. So is there a way that I can massage this, move things around so that these x's are no longer going to contribute to the bad problem? So is there something I do? And remember, multiplication is commutative. You can slide these things around within the denominator and the numerator. It's up to you. So anyone from last class kind of get the idea of what I need to do here? I mean, these are the only things that have an issue, right? These two right here? Yes?
Multiply by 1 over 5 for the first one. That would be sine 5x over 5x.
Okay, so what you're identifying is that, although this, just look at this first x, this is bad. The fact that you have a sine of 5x over here, you can actually use this to help you. If you had 5x down here, right? If you had 5x here, then it would have fallen into this form of sine junk over junk, right? That's what it would have looked like. And the junk would have matched, right? That doesn't even look like the same word. Junk, okay. So what would our junk be over here? Or what would we like our junk to be here? 5x. So we want 5x here, right? We don't have a 5 anywhere here. Now, we can't pull that 5 out, right? I just said that. So we don't have a 5 here. So I would have to introduce a 5 on the top and bottom. And that's okay. I can always do that. How about an x? Do we have an x? Yeah, we have one right here. So let's just use that x, put it over there, and then it won't be a problem anymore. Make sense? Now, at the same time, well, are y'all okay with that?
So you're going to multiply top on the 5?
I am going to multiply top and bottom by 5 to generate the 5 on the bottom that I need. I already have the x I need. And that will take care of this, right? But it still hasn't taken care of this. So can I use this x somehow? Yes, I have this one also sitting here, right? I've already used that one, but I have this one. So I'd really like to have a 3x down there. I already have an x. I just need a 3. So I'm going to come in with a 3 and 3. So on my next line, or I can just do it right here, I'm going to multiply by 5 over 5 and by 3 over 3. So you have to understand why I'm doing that. Is everyone clear on that now? Why I would do that? So I think what I'll do is on the next line, I'm just going to rewrite everything. All right, so let's, we're going to have sine 5x over what? 5x. Now keep in mind, when I do that, I'm going to be using this 5 and that x, right? Those are going to be slid over to that side, right? So I've got 5x here times 1 over cosine 5x. I'm actually not even going to touch that, right? I'm not even using that as part of the problem. It's just there. And then this sine of 3x, I'm going to introduce on the bottom the 3x. And that was this 3 and that x, right? Have now moved over. So what's still over here? Right? I've rewritten these 3 things. I've got 1/4. I've got 5 over 1, or just 5. I'm going to put 5 over 1. And then here I have 3 over 1 because the 3 went over there. So 3 over 1 like that. Okay. Questions? We're not done. Now you take the limit. All right? Now you take the limit. So at this point, I'm not going to write limit anymore. What is this headed towards? 1, right? That's why we did this, right? So we could use that property. 1 times. Now, what about this one? Well, 0, right? You're letting x become 0. 5 times 0 is 0. Cosine of 0 is 1. So you get 1 over 1 here. You don't have division by 0 there. That was never the problem, right? And then here, what does this one head towards? 1 also. This is all multiplication. And then 1/4, 5 over 1, 3 over 1. So at the end of the day, what do we get? 15/4. Which is almost 4, right? 3.75, something like that. So you have, if you were to graph this function, which was a very complicated looking function, right? Tangent 5x times sine 3x over 4x squared. If you graphed it, at 0, it would be undefined. However, from both sides, it would be approaching 3.75 from both sides. Make sense? Okay. What else do I want to kind of illustrate here? Let me just make sure you kind of understand something. One of the things that students kind of, because you're thinking about, oh, I need to remember this property, is that whenever you see sine x over x, you think, oh, that's 1. It's not what I'm saying. I'm not saying that this is 1. I'm saying that if x approaches 0, this expression approaches 1. The difference between these two is that this is a limit, this is not a limit. In fact, if I let this go like limit x approaches 2, your answer is not 1. Your answer is sine of 2 over 2, which is just some number. The only way that this expression turns into 1 is if you're taking the limit as x goes to 0. So these things in here have to be going to 0 for this to work. Understand? Okay. All right. That's pretty good. I will let you. Well, let's do one more. One more. Let's do the limit as x approaches 4 of tangent x minus 4 over sine Okay, I'm going to let you steer the ship here. What do you want me to do? Pardon me?
Check it forward.
Check it. Check to see what happens if you just try and plug 4 in. Okay. If we plug 4 in, we're going to get tangent of 0 on the top, right? And if we plug 4 at the bottom, we get sine of what? 6. Okay, what's tangent of 0? 0. And what's sine of 6? Well, it's not 0, right? It's whatever sine of 6 is, which is some decimal. We could figure out what that is on our calculator, but it's not 0. So what now?
It's just, the limit is just 0.
The limit is just 0. What you have here is 0 over a number, right? That's not 0. This is not 0. So you don't have the bad situation. All you have is 0 divided by a number, which is just 0. So your answer here is 0. The moral of the story is, you see this, you start thinking, oh, I'm going to have to start peeling everything apart. You start doing all that, come to find out that there really was never a problem to begin with, right? So always pay attention. I think this happened last class too. There was a problem that I put up, and we wanted to start factoring, but wait, we didn't have to. It went right away. So always, 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 always check this first, all right? All right, let me give you one that actually does require some work. How about limit x goes to 0 of tangent pi x over tangent 5x. Okay? So what's happening here? What sort of form do we have here when we take this limit? What's happening on top? 0, bottom? 0. So this is bad. Since this is bad, we're going to need to do some sort of algebra. So how about peeling this thing apart? Why don't you take the next, I don't know, 30, 40 seconds to just peel it apart. Make sure you peel it apart. See if we both peel it apart the same way. Don't start introducing things. I want you to just peel the whole thing out first. I'm going to do it up on the board while you're sitting there. Okay, so I don't know if you got to this, but I've put it up here. First thing I did was I've ripped these two apart, just pulled them like this, right? And then I rewrote tangent of pi x as sine of pi x over cosine of pi x. And then I pulled those two apart. So is this fair, this red part? This good? Now, 1 over tangent 5x, I can remember from pre-cal that 1 over tangent is cotangent. So this is the same as cotangent of 5x. And cotangent is cosine over sine. So I have cosine 5x over sine 5x, and I take those and peel them apart. Is that all good? Okay. Now what? What's the next step of the procedure here if we're going to try and follow some sort of procedure? You're going to multiply by 1, but what's going to be kind of guiding you as to what to choose? Like what is...
Check what's the 0 on.
Yeah, where's the bad thing happening? So is this bad? Do we get division by 0 here? No. Do we get division by 0 here? No, because if I plug in 0 here, cosine of 0 is 1, and that's 1 over 1, that's okay. There's no division by 0 here. This one is the one that's causing the problem, right here. So the only way to avoid this being a problem is to do what? What do I need? In order to make this thing not be 1 over 0, I'm going to need something. I need a 5x on top. Now that again goes from last class. Remember, last class I said it didn't matter which way that limit was. You could have sine junk over junk, or you could have junk over sine junk. So this is flipped over from the formula the way I introduced it, but it's okay to have it flipped backwards. So you're saying I need a 5x up here on top. So if I'm going to introduce a 5x, I've got to do a 5x on the top and the bottom. Notice I didn't have an x up here that I could just slide over. It would have been nice, right? To have an x I could just pop over here, but I don't. So I have to introduce it. So I'll introduce it in a different color. I'm going to introduce 5x over 5x. Y'all okay with that? And I'll go ahead and I'll rewrite it. Taking my time here. I really like these problems because these are some of the first problems that you see in this class where you actually have to think about what you're trying to do. It's not something like, you know, in college algebra where you have a quadratic formula, like, okay, I just apply the quadratic equation, you're just like, oh, I'm just going to use the quadratic formula. It's like there's no real thought to that other than I'm going to plug things in. Here you have to actually look at it, identify the problem, where is it happening, and then exploit the weakness within the problem, which is to generate a 5x on the top. Right? So that's a different type of thinking. All right, so here we go. 0, let me go 0. Yes, I'm going to rewrite this all. What's my next piece going to be? What do you think I'm going to write here? 5x over sine 5x, good. And then times 1 over 5x. Okay, so this was that issue that we had, again, last class where we're sitting there, our ship is sinking, we've got water coming in, and we've plugged the hole, right? And then we realized that by plugging the hole, we actually created another hole. See, this is the new problem. We have 1 over 0 again. So it seems like you're like taking a step forward and then a step back, but that's not exactly what's going to happen here. Do you see what I can do? What can I do? Move this x? Where? Ah, over here, this sine of pi x. Even though this isn't a problem, right? This was never a problem. But the fact that it's sitting there, again, I can exploit the property of the limit of sine junk over junk. If I move this x over here, then all I'm really missing is the pi. And I can always introduce a pi over pi to generate the pi I need down there. So what should I put in over here? Pi over pi. All right. And so this will be my last line that I write before I actually take the limit. I'm going to have limit x approaches 0 sine of pi x over what? Pi x. And remember, by doing that, I've used this x and I've used this pi up, right? They're no longer going to be down there. Everything else, I just write. Okay, what's my last two pieces here? 1 over 5 and then pi or pi over 1, however you want to write it. All right. Isn't that clever? Okay, this is equal to limit or no? Should I write the limit? No, because I'm actually going to take the limit now. And this one right here is headed where? 1 times 1 again, because that's 1 over 1, times 1 over 1 again. That's kind of boring. Times 1 again, right? So now finally, just pi over 5. So your answer is pi over 5. There's only a few problems in the book that cover this topic. That's one of the reasons why I'm not a huge fan of this book. The author is great, James Stewart, great author. But this is kind of like a condensed calculus book. This is Cal 1, Cal 2, and Cal 3, right, all in this book. And I think this is a great book if you've learned calculus already and you want to have a good calculus reference book sitting on your bookshelf. This is a good book. But when you're learning calculus, I'm not a real big fan of this. And I'm thinking of this because there's like maybe 6 or 8 problems like this in this book. But in a more expanded calculus textbook, there would be like maybe 20 problems. So, yeah. So that's why I assign almost every single one of them in here, because if it were my choice, I'd give you 20 problems like this to work on, because these are great problems. This really makes you start to think, you know, in a different sort of way, like I was saying a second ago. What do y'all think of this? Does it seem a little different? Yeah? It should seem a little different. All right, that's it. We're going to move out of this section, and we're going to start. We're actually going to jump right now. We were in where were we? We were in 1.4. Where are you? Forgot my mouse down in my office. We were in 1.4, and we're going to go to 1.6 instead of 1.5, and then we'll go back to 1.5. Now, I need to look at our calendar real quick, our schedule that shows you what your homework. Oh, wait, it doesn't show you what your homework problems are. I'm working on that still. At some point within the next week, I will have a document to give you that'll have all your homework on it, okay? On the schedule, it says that we're supposed to cover 1.5 today. So I'm flipping it. We're going to do 1.6 today and then 1.5 next week, all right? So now we're going to talk about limits involving infinity. And maybe before we actually do that, we should talk about infinity. So what do you know about infinity? What have you heard? What is your understanding of infinity? It's very big? It's very big. So is infinity a number?
Yes and no.
Yes and no? But that's not a good answer. That sounds like Google.
Right now, Google up there.
Is that infinity though?
No.
No. So infinity does. I've taught I have an 8-year-old daughter. Since she's been about three or four, I've been telling her infinity is not a number. I want her to understand that. So, what's the biggest number? It's not infinity. Okay, infinity is an idea. Okay, it's a concept. It's a thought. Okay, it's not like the number 5. Number 5, we have very, very clear understanding of what 5 is. I can count out $5 bills, right? I can count out 5 pens. That's very, very concrete. We can see it. But infinity is the concept that something is growing without bound. It's just getting bigger and bigger and bigger. So your number line, right? 0, 1, 2. If you just keep going forever, you are headed to infinity. You're never going to get there, right? And you can't ever stop and say, yep, that's the biggest one. There's always one bigger. So infinity is not a number. It's an idea. So what we're going to be talking about now are limits that involve this idea of infinity. Everything that we've done so far, graphically, like your quiz, okay, gave you -3, and I don't remember what it looked like, but whatever, I'm just going to make it up. I think it was something like that. When I said, what's the limit as x approaches -3 from the left or from the right, what we were headed towards, right? What x was headed towards was a nice number, right? A nice fixed number. And our graphs, when the limit existed, right? When the limit existed, our graphs were headed towards nice numbers, right? Like from the left, maybe it's headed towards 3, and from the right, it's headed towards 2. But what happens when we have graphs that don't behave like that? What happens when we have graphs that have asymptotes like that? So now if I'm headed this way, right, let's say that this is the number 4. If I'm headed to 4 from the right, my function is what? Taking off, right? Headed towards infinity, positive infinity, right? So now this is what this section is about. We want our limits to not be restricted anymore to just finite things. We want to be able to talk about things that grow without bound. And in fact, we would like to know what happens when we approach infinity. So these are two separate concepts, and that's what we're about to talk about. So this section is about two different ideas. The first of which is what we call infinite limits. Come on, let's go. All right, so I'm kind of tethered to my thing because I forgot my mouse down in my office. We've already seen the sometimes. I think that's supposed to say that sometimes. When we take the limit, we get infinity or negative infinity as an answer. So we did do that last class. Do you remember me telling, or was it the last class or the one before? I think it was the first class, where I said, hey, the book might say does not exist, but I'm going to start using infinity or negative infinity. So that was the case where we had a vertical asymptote like this. Okay, so we would say from the left it's approaching negative infinity, from the right it's approaching positive infinity. We've seen this, all right? So this is another example. This was that volcano function, right? This was that volcano. I called it a volcano function because it's supposed to look kind of like a volcano. Our answer to this is that the limit as x approaches 0 of 1 over x squared, that's the actual function, is equal to infinity. Now let's understand why it's infinity. I mean, from the picture it is, right? But why is it, I don't have a plus or minus here, right? Which means what? It has to, if I'm going to say it's approaching infinity, that means it has to be both the left and the right have to be going to positive infinity, right? Yes? Notice also that I have something back from college algebra happening at 0, an asymptote. So if we look at this back from the college algebra perspective, this function 1 over x squared, if you were in college algebra and you were asked, hey, find the vertical asymptotes of this function, what you would do is you would set the denominator equal to 0. Do you remember doing that in college algebra? And if I set x squared to 0, I get 0. So something very interesting is happening at 0. At 0, I have a vertical asymptote, but I also have the limit as I approach it is heading towards infinity. The fact that that's happening, they are connected. Okay, there is a connection between vertical asymptotes and limits going to infinity. Let's look at a different example. Okay. So this right here, this is not solid. I told you all that first day. This is the computer's making mistakes. So I have a dotted line there. This is the function just 1 over x. So what's happening here is that the limit as x approaches 0 does not exist. Why does that limit not exist? Because it's there's no plus or minus up here, which means you have to look both left and right. What's the limit from the left-hand limit? Negative infinity, I'm just going to put here negative infinity, and then this limit over here is positive infinity. And those aren't the same, right? Like negative infinity on a number line, that's like go that way forever, and positive infinity is go that way forever. So these are two different things. The limit doesn't exist, but do you still have a vertical asymptote here? Yes. You still do. And I said that there was a connection, so I haven't made the connection yet, but I want you to see that even though the limit doesn't exist, we still do have a vertical asymptote here. Okay, so in college algebra, we had a definition and a way of getting the vertical asymptote, but here in calculus, we have a different sort of definition. We say that the line x equals a, remember x equals a is a vertical line, like x equals 2 is a vertical line. Okay, the line x equals a is called a vertical asymptote of a function f if any one of the following are true. If any of these are true, we have a vertical asymptote at a. So this says if you come in from the left side of a and it goes to infinity, you have a vertical asymptote. It does not matter what's happening from the right. If just that one condition holds, you have a vertical asymptote. If you come in from the right and you get infinity, so you come in from the right, you go to infinity, then you have a vertical asymptote there. Understand? If you come in from the left and it goes to negative infinity, then you have a vertical asymptote. Or if you come in from the right, it goes to negative infinity, you have a vertical asymptote. And of course, the last two say what? From both left and right, you go to infinity, or both left and right, you go to negative infinity. So basically, this is saying this. If you have a graph, let's say this is A. If you go to infinity on this side, you don't even care about what's happening here. You can say you have a vertical asymptote. If you have the right going to infinity, you have a vertical asymptote. You don't even care about what's happening here. Just one of those has to hold. And of course, if they both go, then you still have vertical asymptote. So you see it's kind of like a weaker condition. You just need one of the two sides to go to infinity. If they both go, fine. If they go opposite, that's okay. You just need one side and one side only. So I think I have an example here. Look at this one right here. Let's look at 2. Okay, this is 2. Let me draw a dotted line so you can see this here. Can you all see that this is 5 here? 4, 3, 2, 1. What is f of 2? Looks like it's 1, right? Our function is defined at 2 to be 1. What's the right-hand limit? What's the right-hand limit? 1, right? So the limit as x approaches 2 from the right of this function is 1, right? Now, what is the limit as x approaches 2 from the left of this function? It's positive infinity, right? Does this function have an asymptote at 2? Yes. Yes. See, back in college algebra, every asymptote you ever had, your function was never defined at the vertical asymptote. It always went like that, or like this, or like that, or like that. But at the asymptote, you did not have graph, right? In calculus, we're changing the definition a little. Well, we're not really changing definition. It's just that in college algebra, you only talked about rational functions. So rational functions won't ever be defined at the asymptote. But if you open up the world to all the other functions, it's possible to have a function that is defined at the same point, or at the same x value that you have a vertical asymptote. It's possible. So we do have a vertical asymptote here. With me? All right. Let's not overcomplicate it, because it is what it is. All right. Let's do a couple of examples here. Let f of x equal, let's start with the rational function because I think that will be worth our time here. Okay, I've just given you a rational function. I want you to find the vertical asymptotes. I'm going to abbreviate it. Find the vertical asymptotes of this function. And then find the left and the right hand limits at each vertical asymptote. All right, so let's try and figure out where we have something interesting happening. So what would you do to try and find the vertical asymptotes of this function? You'd factor the denominator out first, right? So let's factor, this is x plus 3 over, what is that? X plus 2, x minus 3. Okay, so that factors. Now, do any of those factors cancel? No. If they did, we would actually have a whole. Maybe I'll do that as the next example so you can see the difference between the two. But nothing factors out, right? Like nothing, nothing cancels. No factors cancel. So it appears that we're going to have two vertical asymptotes. Where are they going to be? Vertical asymptotes at x equals 3 and x equals -2, right? So all we're doing is setting each of these factors equal to 0. Okay, so we will have two vertical asymptotes because we know this. We know this because of college algebra that this should happen. But what's the left and right hand limits at these? So let's start with the 3. What is the limit as x approaches 3 from the left, right, of what? That, right? That function. So I'm going to put it right here. X plus 3 over x plus 2 over x minus 3. So I'm about to figure out what this function's doing as we approach 3 from the left without the graph. Without the graph. All right? Here we go. This is going to be, I think, kind of interesting, I hope, to you. This is going to be interesting. This is kind of, to me, this is, again, this goes back into that whole idea of we're going to start thinking a little different than we have in the past. What is this limit right now if I just plug in 3? If I just try and plug 3 in, what happens? On the top, I get what? 6. And on the bottom, I get 0. Now, I told you 0 over 0 was bad, didn't I? But I never talked about 6 over 0. 6 over 0 is bad. I agree it is bad, but it's a different kind of bad than 0 over 0. It's different. So the form that we have here is that we have a fixed number over 0. I want you to look at it that way. Not 0 over 0, fixed 6, right? It's a nice number divided by 0. Anytime you have this situation, when you are taking a limit, anytime you see this situation, there are 3 possible outcomes. That's it. There's only 3 answers that can be. All right? Here are the 3 answers. Do you have any guess as to what they might be? If you have a number on top that's fixed and a number on the bottom that's getting small, what happens to that fraction? If you have a number that doesn't change and a number on the bottom that's getting smaller, what does that fraction do? It grows. So this answer is either going to be growing, which is what? Infinity. Or the fixed number on top didn't have to be 6, right? It could have been -6. And then you have -6 divided by a small number, which should be a very big negative number. So that would be what? Negative infinity. Or the last possibility is that from one side it's doing one thing and from the other side it's doing something else, which means that they would go to different places. So you could have does not exist. Okay. You all right with this? I'm going to recap because this is like fundamentally important for the class. If you see 0 over 0, right? In a limit, right? All of this is in a limit. In a limit, right? In a limit. If you see 0 over 0, this is what? Bad. And what do you do when you see this? Algebra. Algebra or some trick, right? That's what you're going to do? If you see in a limit a fixed number over 0, then this is still bad, right? But this tells you right now that it's the answer is going to be this, or does not exist. Okay? So we're starting to like categorize how these limits look. So far, we've kind of have an idea of what we would do here. This is the first time we've seen something like this. All right? Okay, so how are we gonna determine which of these answers it is? I know it's one of these, but I don't know which one. So now we just have to kind of play around with numbers. We just have to mess with this. So we are approaching 3 from the left side, right? Correct? So I'm going to just draw a number line to get a visual of what's happening here. Here's 3, right? And I'm going to approach it from the left side. So I'm going to be coming into 3 on my x-axis, and my function is doing something, isn't it? And that's what I'm trying to figure out. So somebody give me an example of a number that's to the left of 3, but pretty close to 3. 2.9, 2.99, right? And then we could go all day, right? So let's just, for the sake of getting an idea, right? 2.9. 2.9. Imagine now taking this expression and plugging in 2.9 for x everywhere. All right? Just imagine what would happen. Tell me about this value right here. Would it be positive or negative? Positive. And that's all I'm going to look at right now, is whether or not it's positive or negative. Because I know it's either this, this, or this, right? I'm going to see if I can determine if it's positive or negative. So if I plug in 2.9 right here, I get a positive number on top. Over. If I plug in 2.9 right here, what do I get? 2.9 plus 2 is like 4.9. So that's positive also. Times, and now if I plug in 2.9 minus 3, that's negative, right? So this would be a negative number. And so you have a positive number divided by a negative number, which means it must be negative. Agreed? Yes. So this must be a negative number. And the only answer that makes sense over here then is what? Negative infinity. Why not this though? Why?
Because we don't know if it's approaching the same place for both sides yet.
Okay, so but what does this limit, the limit that I'm looking at right now is only approaching from one side, right? It's only approaching from one side. So I don't have to worry about the does not exist happening, because this will only happen when it goes to two different places from two different sides. So since I was only doing a one-handed limit from the left side, it really eliminated it down to this. And I know then that it can only be the negative answer, so it has to be negative infinity. Yes?
Well, what if it's like oscillating coming in from the left side?
What if it's oscillating how?
So like how you get
Like a
the
sine
example.
wave or a cosine
sine
wave.
I can
by
show you.
the,
I
can
think
show you.
it would only be in a section, and you'd only take like a...
Okay, well, I think I know what you're getting at here. The reason why I know that it's not oscillating is because of the form that we have right here. As x goes to 3, right? As x goes to 3, my function, the numerator goes to 6, right? And the denominator gets small. This is, again, fundamentally important you understand what this is telling you. The numerator is going to a fixed number. The denominator is shrinking. That can't oscillate. Because to oscillate, what would have to happen is something like the numerator gets bigger and then smaller and then bigger and then smaller, right? So that the whole function moves up and down. But this is telling me that's not happening. This is telling me that the numerator is just like, hey, I want to be 6, right? So I want to be 6, I want to be 6. And the denominator is like, well, I'm going away. I'm going to nothing. And so this fraction is getting huge, so the function is taking off. But the question is it taking off like that? Or is it taking off like this? Is that kind of resolved? This is the part that tells you. Pardon?
We won't see that situation basically, where it's oscillating.
You might see an oscillation. Yes, they will come. But when we do this thing, this little arrow to try and figure this part out right here, it won't be doing this. Okay? It won't be doing this. It'll be a different sort of expression, and then we'll say, okay, when we see that, what are we thinking? All right? Anytime you see fixed over 0, though, you can't have oscillation. These right here that I've referred to, these two things right here, these are called limit forms. I'm going to give you this later, but we may as well start getting some language down. The form of the limit that we had there, the two that we've looked at is 0 over 0 and fixed over 0. Those are the two forms that we've looked at. We're going to look at like 7 or 8 different ones. Okay. Can we keep going?
Keep going.
All right. The left-hand limit of the first vertical asymptote was negative infinity. I never put the answer down here, but it was negative infinity. So this limit right here, this limit is negative infinity. Now, let's do the next one. Let's do the right-hand limit. Limit x approaches 3 from the right this time of x plus 3 over x plus 2 times x minus 3. Same story. Let x go to 3. What happens when x goes to 3? You get 6 on top, and on the bottom you get 0 again. See, it looks exactly the same as this one, doesn't it? But it's not. There's something subtly different happening on this one. And it all comes down to the side we're approaching from. So the way that I like to do this is I like to draw a little number line. I like to mark down 3. I like to imagine coming in from the right. And then I want to go ahead and pick a number that would be to the right of 3. So 3.1, good enough. 3.1. And I'm going to plug that in here, 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 and see only what's happening with the signs. So if I plug 3.1 in here, I'm going to get positive. If I plug 3.1 in here, positive. And this time when I plug 3.1 in here, I get positive. And if you have a ratio of all positives, your answer is going to be positive. Yeah, positive. And therefore, it can only be positive infinity. It's weird, right? I mean, because like, to evaluate this limit, to figure out what's happening, I'm actually not really doing any like algebra, right? I'm not sitting here like, I'm going to factor, and no, I'm like thinking. And this is my thinking on paper. Y'all see that? So that's the type of work that you have to have for a problem like this. Your thoughts somehow expressed on paper, how you came up with this. All right, let's do the next vertical asymptote. This one, there's a little tricky part of this one. Let's see how y'all do with it. I want to do the limit. You tell me. X approaches -2 from the, which side? I don't care which one we do first. Left? So I put a little, what here? Little minus sign. And then I'm going to write the function, x plus 3 over x plus 2 times x minus 3. And then let's go ahead and plug in and see what happens. Let's see what sort of limit form we get. My bet is we're going to get fixed over 0 again. Let's see. So plug in -2. -2 plus 3 should be 1, right? So on top we're going to 1, and on the bottom, -2, and here we get 0. So we get 0 here. And this is fixed over 0. So we're back in this ball game right here, right? We see fixed over 0. We start thinking it's going to be one of these 3. I can eliminate this one because it's only from one side. So it's going to have to be either infinity or negative infinity. So what should I do at this point? What's that? Draw a little number line, okay? And then draw -2 on my little number line. This drawing is just to help me pick a number. So I need a number on which side of -2? The left side. So I'm coming in from this side right here. This is the part that I said is a little tricky. Just be careful. -2.1, not -1.99, right? Think about where 0 is. 0 is over here, -1, -1.9, then -2, then -2.1. So it's actually -2.1 that we're going to use. Y'all see that? That didn't happen over here because we're comfortable with the positive part of the number line. Over there, we have to kind of think about it a little bit. And I take that and plug it in. Let's see what happens. Up here, -2.1 in here, get positive on top. Okay, here, plug in -2.1. Negative. Here, negative. 2 negatives on the bottom make a positive. Positive is positive. So we get positive infinity is going to be our answer here. So coming in from the left at -2, we're going to be going to positive infinity. So my answer here